Alright, guys, we're going to look at percent composition, empirical, and molecular formulas. Let's take a look at this joke. I think I can truly say that in all this book we have the elements of a first-class thriller. It's 98.7% carbon, 0.55% aluminum, 0.09% silicon, 0.23% oxygen. You all can read, which are actually mostly the basis of the human body. That's a percentage breakdown by element of what's in the human body. We'll figure out how to calculate the percent composition or that type of idea, but for different elements and other things as we go forward. So learning targets. These are things that are useful to keep in mind, so it's helpful to know what to study, to look at, or trying to do. So our first one, I can determine the percent composition of each element in a chemical compound. Also, I can determine what the empirical and molecular formulas are for compounds. I don't know what those are yet, but you will soon. Alright, so how do we calculate this percent composition thing? It's got a formula, but it shouldn't be all that hard. You've done something similar to this probably in math class before. So when we're calculating a percent of anything, you need to put the stuff on top, stuff you're looking for, they're trying to measure, over the total stuff on the bottom, times 100, because it's a percent. So percent composition, you may write this down as a definition, it's the percent of our stuff's mass is made a part of. So we're looking for percent of chlorine in a compound. You take the chlorine's mass over the total mass of the compound times 100 to get the percent of chlorine. We're going to look at a fairly normal example. We're going to talk about a weird example. We'll look at some chemistry examples. Alright, so let's look at it. Percent composition of a hamburger. Alright, percent composition is kind of like asking what percentage of this cheeseburger's mass is from the beef, what percentage is from the cheese, or from the bun, or from the tomato, or from the lettuce. Each one of those percentages has a number. It should all in theory add up to the total, which better be 100% in the end. Alright, so how do we calculate this? We have our formula here on the bottom. Let's focus on the meat, because that's why I really like to eat burgers. So let's imagine we have a quarter-pound burger. This means that beef weighs about a quarter pound. And if we imagine the whole burger weighs a half a pound, then we take our stuff, our beef, and we divide the mass of the beef by the mass of the whole burger and multiply by 100. We get 1/4 pound divided by a half pound times 100, we get 50%. It's 50% of its mass is from the burger. Pretty simple. The same thing if we're looking at the percentage of our body mass that comes from our arms. If we were able to rip off our arms, which would be really painful and bloody, but if you could, and you were to mass your arms, let's say my arms weigh 20 pounds. And if I weigh 160 pounds, we took 20 pounds on top, divided by 160 pounds total, we could calculate the percentage of my body mass that came from my arms. It'd be the same idea, if a little bit weird. So if we do it in chemistry, there's a bunch of steps you can follow, but it's the same idea. We're going to calculate the molar mass, which we just did last unit, of the molecule. That's going to be your total molar mass. It's the mass of all the elements added together. So whatever that formula is, you have the mass of every single atom all together to get your grams per mole, molar mass. Then we need to calculate the mass of each individual element in the molecule. So if it's H2SO4, you might add up all the H's together, and then all the S's together, all the O's together. And you did this individually for step 1 to calculate the molar mass. You just didn't keep them separate. You put them together. So you showed your work on paper. You have this. It'll make it easier. Step 3 is to set up that percentage equation that we used on the last 2 slides. The stuff over total stuff times 100. So if we look at this one, what's calculate the percent composition of magnesium carbonate, so MgCO3. Well, we need to find the molar mass. So 24.31 is the molar mass of magnesium from the periodic table. 12.01 is the mass of carbon from the periodic table. And 16 is oxygens. We're taking 3 times 16 because we have 3 oxygens in MgCO3. That 3 applies to the O, not to the C, because there's no parentheses. we have total molar mass of 84.32. So to find the percent composition of any one element, take the mass of just the magnesium over the total times 100, which will get us 28.83% magnesium. Same thing for carbon. Carbon's mass over the total mass times 100 gets us carbon's percent. Same thing for oxygen, but remember, we don't have 16 here for oxygen's molar mass because it's 3 oxygen. So it's 16 times 3, which is 48. So 48 divided by 84.32 gets us 56.93. Now if we add up our 3 percentages, what should that come out to? You should have said 100%, because if you add up all the elements together and it doesn't make 100% of the molecule, what'd you do? How'd you destroy it? That's impossible. You can't play God. It's got to add up to 100%. Alright, a few definitions before we move forward. Empirical formula. It's the lowest whole number ratio of atoms in a compound. Versus the molecular formula, which is the true or actual number of atoms in each element in the formula of a compound. That's what we've been mostly looking at so far. So, some examples to go with that. Remember, you can always pause if you need to. So the molecular formula of this compound is C6H6. We can divide both of these subscripts, just like you do in math. You can reduce it to the lowest form. So C6 and H6 can both be divided by 6. If you do that, they're reduced down to just CH. When you do that and reduce it, that gets you the empirical formula, the lowest whole number ratio. So C1H1, we don't write the ones if it's just a 1, gets you the empirical formula. So we go from C6H6 for the normal numbers, the molecular formula, divide them by whatever number they can both be divided by, gets us an empirical formula of just CH. Right. Why do we need empirical formulas? Well, they allow us to find molecular formulas, which is how we actually make compounds. So an example is something called adipic acid. It was discovered in the 1940s. It's used to make a ton of stuff. Nylons, like the nylons that women wear, plus also a thing on like clothes, guitar strings, parachutes, a ton of fabrics and medicines, and also adds that tart flavor to foods. Problem is, it's extremely hard to find in nature. It's not common. But it's used in so many things. So scientists wanted to find a way to make it, but when they find it in the lab, they only get the empirical formula. They need to find the molecular formula to be able to make it. Once they found out how to do that, they were able to produce, well, today over 5 billion pounds is made in a lab. When you make it by hand, by humans, it's called being made synthetically. Alright, so how do we find an empirical formula from our lab data? We're going to assume we start with 100 grams of the chemical. Now, if we use percent by mass, like we did from earlier in this presentation, we're going to find grams of the element. Okay, so once we have the percent by mass like we did before, and we're going to use that to find the grams of each element. We're going to convert that mass of each element into moles, what you've done before, grams to moles. We're going to divide each of those numbers that we get for answers by whichever answer is the smallest. So we get an answer of like 1.2 and 0.67 and 14. Divide them all by that 0.67 because it's the smallest. Once we do that, we'll round those answers to the nearest whole, like decimal, 0.25, 0.5, 0.33, 0.75. Should be a nice fraction. We'll multiply each of those mole numbers by the same thing so that those decimals go away. So it's 0.5, that's half, so you multiply by 2. And it's in a decimal of 0.25 or 0.75, you multiply by 4. 0.5 we just said, you multiply by 2. It's 0.33, you multiply by 3. You shouldn't have any other numbers that aren't those. Then you simplify all numbers you have to the lowest whole number ratio. That's what makes it an empirical formula. It'll be easier here with an example. So let's look at an example here. Alright, so the adipic acid example we looked at, it contains 49.32% carbon, 43.84% oxygen, and about 7% hydrogen. So first step, take those percentages by mass for each element to find grams. So if we take stuff over total stuff and times by 100, there we go. So then take our mass of carbon, which in this case, if we look at the 100 on the bottom and the 100 on top, they cancel out. So our mass of carbon is the same as a percentage. 49.32 is going to be grams of carbon, and 49.32 is a percentage of carbon. So we assume it's 100% and 100 grams. We can just basically skip that step and turn all the percentages directly into grams. It saves you time and energy. Okay, so now we've got our grams. 49.32 grams of carbon, 43.84 of oxygen, and 6.85 grams of hydrogen. That was step 1. Now step 2 is turning them all from mass, grams, into moles. So we do that by canceling grams of carbon and going from grams of carbon into moles of carbon. Notice the mole of carbon, grams of carbon, cancels, we have a number. We do that for all 3 of them using their molar masses off the periodic table. We get 3 answers. One for moles of carbon, 1 for moles of oxygen, and 1 for moles of hydrogen. Then we take all 3 of those answers. Oh, go away, face. There we go. We take all the answers we got and divide them each by the smallest answer we had. In the last case, if I flip back up, our smallest number here is 2.74. So we're going to divide all of them by 2.74. We take 4.11 by 2.74. We get 1.50. When I take 6.78 by 2.74, I get 2.47, which is close enough. We'll round that up to 2.5. And if I take 2.74 by 2.74, I get 1. As you should notice, you'll get one of the numbers has to go to 1 every time. These numbers tell us the subscripts for the empirical formula, so the little numbers next to the atoms. Notice those decimals, 1.5, 2.5. Can you have half of an atom? I've got 2.5 atoms. No, atom literally means indivisible. You can't break apart an atom. So we got to fix that. So if we've got 1.5 carbons, 2.5 hydrogens, to get rid of that half, we have to multiply them by something. So 1/2 is 1 over 2. If you multiply by 2, you can then make that half go away. So it's 1.5 times 2 gets us 3. 2.5 times 2 gets us 5. And what you do to one thing in an equation, just like in math, you must do to everything in the equation. So 1 times 2 gets us 2 oxygens. Now that these are all whole numbers and can't be divided by anything else, or can't be divided by the same thing, we use those to give us our empirical formula. So carbon has 3, C3. Hydrogen has 5, H5, the one I covered up. Oxygen has 2, O2. That's your empirical formula. Now last one, if we're going from empirical to molecular, we have to get it from larger to bigger. I'm going to skip the analogy for a second. If you want to read it, you are more than welcome to pause it and read it. Go for it. Okay. Here are your steps. I'm just going to walk you through how to do it. Again, you're welcome to read them and write them down. If it helps you, that's great. Okay, the molar mass of adipic acid is 146 grams per mole, as calculated in the lab. That'll be given to you in the question always. They also have to give you the formula of the empirical substance. So first we have to find the molar mass of this empirical formula, which you guys know how to do. Then you're going to take the molar mass of the molecular formula and divide it by the mass of the empirical formula. You should get a whole number ratio or really, really close. So 2, 3, 4, 5, 6, something like that. Then you take whatever number you got, and that number gets multiplied into all of these little subscripts in there to make it be a final answer. So instead of C3, it becomes C6, H5, H10, O2, O4. And that's all you have to do to find the molecular formula. The end.